So we have two big items today, which we're going to do before and after the break. The first item is the recursion theorem. And then the second item is Gödel's incompleteness theorem for arithmetic. All right, so let me, this is what happens when you try to do things in an armchair. Let me begin with the recursion theorem. So this is a somewhat funny term because you might wonder, what has this got to do with recursion? Oops. But that will become clear in a minute. In the early days of computability theory, people really emphasized the role of recursive programs because that's when they realized it's with recursion that you can get the full power of computable functions. And so the subject itself used to be called recursion theory. And that's why you have phrases like recursive set, recursively enumerable set, and so on. And later on, they realized computability theory is a better name for it. But this theorem is still called the recursion theorem. So let's imagine that we have P, which is a program. And then I'll use angle brackets P to mean code of the program. Okay, so I don't care how you represent the code. Maybe it's a string in a programming language. Maybe it's just a Goedel numbering. So it's just an integer. I absolutely don't care. Whatever is convenient, we will assume. And now we imagine a crazy two new primitives. So one is called obtain. So this says, give me my own source code. So this allows a program to access its own source code. Okay, so we'll also give you something called run P, which basically means run this program. So let's do some examples of what I can do with this enhancement to my programming language. So this is a program that I'm going to call P1, and its source code says obtain, get your hands on the source code, and then output so there you are, your basic self-reproducing program. Now you might look at this and say, well, this is a bit flaky because I mean, where are we going to get this obtain thing from? It just sounds like science fiction, right? But basically, the recursion theorem says you can implement this with ordinary Turing machines. So let me give you an example of a self-reproducing program in English. Why is OneNote behaving like this? Of a self-reproducing program in English. So English is the programming language and you are the hardware. So here's the program. write the following sentence twice. The second time inside quotes. And then you write the following sentence twice. The second time in quotes. So there you are. If I show this to a person and say, carry out these instructions, what will they produce? Exactly the text of the program. So that's how you write self-reproducing programs. And example one is how you would write self-reproducing programs if you had access to your own source code. So let me do example two of using obtain. So here you say, so this program we're going to call P2. And P2 has input is a word in sigma star. This is not part of the program text. This is just my description of the input type. So what is the actual program text? If the word equals epsilon, then output 0. Else, obtain P2. Run P2 on tail of the word. So tail of the word means the word with the first thing removed. If you get n, return n plus 1. So that's the program. And what does it do? P2 recursively computes the length of W. And this you can see is how recursion works in programming languages. They say, call the procedure on this other argument. That means somewhere the code of the procedure is available for the program to call. So you see, it's not so mysterious as when I first introduced it and said, obtain the source code. So, and indeed, this is kind of what's happening when we implement recursion. Okay, so the whole point of the recursion theorem is saying ordinary Turing machines know how to do this already. It's not a new feature that we've added. So let me state the recursion theorem. So theorem. Let T be a Turing machine that computes a function little t. So the convention I'm using is that capital T or capital letters will stand for machines. Angle brackets around it will be code for that machine. And lowercase letter means this is the function that the machine computes. Okay, so little t is the function that the machine computes. So little t is computing some function from pairs of strings to strings. And okay, maybe I should emphasize this is possibly a partial function. Then there is another Turing machine which we shall call R, which computes a function of one argument, also possibly partial, such that for every word running R on that word, so little r says this is what you compute, is the effect of running T on two arguments. The first argument is the source code of R. The second argument is this word W. So this theorem says you can always give a machine its own source code. And there's nothing magical about it. Okay, so I remind you, R and T may be partial functions. All right, so let's look at some cases of this. So I'm going to prove this theorem using a lot of pictures, actually. So first, some notation. So I'm going to show this Turing machine T as a box. It's got two inputs. I'll call them X and W, just strings. And what is its output? Well, that's the function little t of Wx or XW.
Professor, sorry. Someone asked whether T is supposed to be taking the source code of R and not its own source code?
Correct. T is taking the source code of R.
Okay.
But this is the point is R is behaving like something that has access to the source code of R. You see, because on the left-hand side of this equation, it says R of W. So running the machine R on W is like running another machine that has access to the source code of R. Okay, so now, so that's how we generically write what a Turing machine does. The special case of this is when T, instead of getting a generic string X, gets actually the encoding of some Turing machine. Okay, so this is just a special case. And all I'm saying here is one of the strings could just be the encoding of a Turing machine. All right, this is just notation in pictures for what I was saying in formulas before. So how does R behave? So R behaves like this. There's a machine T which gets access to the source code of R and W, and then it computes little t of R W. But we said that this is exactly the same as the machine R, which computes okay, because we said R of W is exactly T of applied to source code of R and W. So this is the sense in which R actually has access to its own source code. Okay, so R behaves like T, but with the first argument fixed to be its own source code. Okay, so I'm going to start now by proving a simple case of the recursion theorem. So this is going to be a proof of a special case. And I don't actually have to prove the special case first. Special case is just to warm you up. So it depends on a lemma. And this says there is a total computable function, which I'll call Q, from sigma star to sigma star, such that Q of any word is P of W, but not P of W, the code for P of W, where P of W is the Turing machine that writes W on its tape. And stops. Okay, so there's absolutely nothing mysterious about Q. It's clearly a total computable function. The Turing machine that just writes W on its tape. Let's see, I wrote it somewhere. Oh, yes. So imagine I have these transitions. Delta Q0, looking at a blank cell, it goes to state Q1, writes F, and goes one step to the right. Then on state Q1, looking at blank tape, it goes to Q2, writes O, and moves one step to the right. Then Q2 on blank tape goes to Q3, writes O, and goes one step to the right. And then Q3, looking at blank tape, goes to the accept state, doesn't do anything, and goes one step to the left and stops. So what does this Turing machine do? If you give it blank tape, it will first write F on the first cell, move one step to the right, write O on the second cell, move one step to the right, write O on the third cell, move one step to the right, then sees it's blank, move back here and stop. So it's just written foo on the tape. And you can see the program for it. It's a small little thing. So it's not very difficult to imagine. If I wanted to write any other string, I could do it this way. So there's nothing mysterious about the fact that it's a total computable function. But I do want to emphasize something. Q doesn't take the machine and run it. It just produces the source code of PW. Because at this point should be clear. Q is a string to string mapping. The input is some string. The output is the code for the Turing machine that will write that first input string on its tape and stop. Okay? It's certainly total because it'll always do this and stop. All right, so this lemma we're going to take for granted. Okay, so now back to our special case. So we're going to use this notation to mean B reads output of A. Okay, so here are two Turing machines and we hook them up like this. You run A, maybe A is something with no input. You just run A, it produces some output. That output is fed to B, then B reacts and does something. So we will use the notation A semicolon B. Kind of how you think about programs. You run A first and then you run B first. Okay. So B expects its input to be of the form encoding of some machine, right? And you might say, well, what if I don't feed it that? God knows, might crash. I'm not specifying, but fortunately, we don't have to worry about that too much because what we're feeding to B is actually controlled by A. So we don't really need to know how B behaves on generic input. Okay, so B outputs. So what does B output? B outputs this very interesting thing. So let's try and understand this. The first piece is just from the lemma above. It says you gave me a string and I produced the code for the Turing machine that will simply write that string on its tape. Okay. But the machine that writes that string on its tape is then fed into the actual machine that you gave me. So you gave me the code of some machine. Now, of course, when I say I gave you the code for some machine, I literally have the code as a string. And so what I do is I say, now I'm going to produce a program that says, take the encoding of M, feed it to M. And of course, I'm not actually outputting a machine, I'm outputting the code. So you see the outside angle brackets. B outputs a string. Nothing is actually being run. It's not like I'm actually taking anything and passing it to M. I'm just saying I'm outputting the code of the machine that does that. Okay, and codes of machines are just strings. So B is a string to string function. All right. So this is really easy to do because we've got our lemma that tells us how to produce this, and the code for M, you just gave it to me. So all I'm doing is packaging those two things together. This thing that I produced from the lemma and this code that you gave me, I package it together and say, right, here's my code package, that's my output. Now, the machine that does all this has some code. So B is just a string. And what's A? A is the machine that outputs the description of B. So let's see how this thing works. We've got our Turing machine A, but we now know what A is. It's not any old thing. It's the machine that outputs this string, which happens to be the description of B. So let's see, what is the output? Well, we just said what it is. It's the description of B. And what does B do? It says, I'm expecting the input to be the code of some Turing machine, and then I produce the thing that writes that code and then feeds it to B. So this is the output. The output is the code of PB followed by B. But PB is what we said A was. So output of AB is code of AB. Voila, self-reproducing program. also can be slightly modified to produce viruses, but let's not talk about that now. With all good things come possible bad things. So indeed, this is the heart of any virus program, the ability to reproduce itself. Okay. So this is a warm-up because it kind of shows you this is how you produce a program that produces itself. But the recursion theorem is more general than that. So, general case of the recursion theorem. All right, what is happening? So what does the statement say? It says, for all Turing machines, for all t such that you have a 2-argument function. So this is maybe a Turing machine with 2 tapes. For all such t, there exists R such that R, when fed with W, also computes this thing. Okay, so this is the general case that we're trying to prove. You give me any t like that, I can construct this R. Okay, so remember how it goes. You give me a t, so I don't have to look at the inside of t. You've given me t as a box. I get to package it however I want. So just some notation first. We showed you the notation for hooking up one Turing machine to another with the semicolon. But sometimes you want to do this. You have a Turing machine with 2 inputs and 1 output. And then you want to take a Turing machine with 1 output and plug it into the first argument, but leaving the second one free. Okay, so the notation for this, we'll write x semicolon y, but we'll put a little superscript 1 to mean I'm plugging the x into the first argument of y. If I want to plug it into the second argument, I'll put a little superscript 2, but in the notation below, that never happens. Okay, so this is the notation. This is the notation for that picture. So I'm going to try to write both the notations and the pictures, because the pictures, I think, were much more intuitive for me at least. This is a constructive proof. So what am I going to do? I'm going to show you R. So I'm going to take T as a given box, and here's R. Okay, so here's the construction of R. Construction of R given T. Okay, so T is given. Now, how do I build R? The answer is very simple. I have to tell you what these components do, but we'll start out using simple components. So there's a Turing machine called A. Which it's similar to the A I described before, but it's slightly modified. Then there's another Turing machine called B, which is again like the Turing machine I had before, but slightly modified. Then this is fed into T. But the second argument And that's it. So this, in terms of the notation I've introduced, is A semicolon B. I don't have to write superscripts and all because B is just a one argument input thing. But then this is fed to the first argument of T. So this notation describes that picture. Or that picture is a picture of this notation. So all I have to do is tell you what the heck are A and B, and then we have to see, does it work as advertised? So simple. A is the Turing machine that outputs the code of B hooked into T. Okay, so what is, that's just this Turing machine. Okay, this is this Turing machine, but it's not outputting a machine, it's outputting the code of the machine. So P is just one of the things that we got from our lemma that says, I can write any Turing machine that will produce a particular string on its tape. So the string it's going to produce is the description of P1 hooked up to T. What's B? So B is a thing that says, give me a Turing machine description. And what I'm going to do is kind of like what I had before, except I need to modify it because I'm feeding it to a 2-argument function. Okay, so that's B. It reads a Turing machine description. It produces the code of the Turing machine that will write that description on its tape. Then it will pass it as the first argument to the Turing machine description that it was given. And this is, of course, easy because you're giving it the description of M. You don't have to reproduce it. And then, of course, you're packaging this all up. It's not that you're actually producing the machine. You're producing the code of the machine. So you have to keep your eye on the type system here and distinguish between machines and the code that produces that machine. So the output of B is a, and I'll put this in red, description of this machine. Right, as it says, feed it to the first argument of M. Okay, so it's not outputting this machine, it's outputting the description of this machine. Okay, good. So now let's look back at our construction of R. So R is, if we use our notation, it's A semicolon B semicolon superscripted 1 T. That's all it is. So let's draw it again and look at it closely. There's A. You can make a slightly smaller A. So there's A, which is, of course, P of B1 fed to T. And there's some output which I'll temporarily call 1. Then we have B, which I've described above. It produces some output which we'll call 2. We will work out what 1, 2, and so on are in a minute. And then all this is fed to T, which is getting on its other input some word W, and the output is something which we need to work out. So let's work these things out. So what's 1? This is the output of A. This is, of course, just the description of this machine. Because if you look at what A was said to be, it says, I am the Turing machine that outputs this string. And what is this string? It's the description of B hooked to T through the first argument. So that's exactly what A outputs. Output of B. Well, B says, I'm expecting a Turing machine description as input. By golly, I've got one. And what am I supposed to do? I am supposed to first output the code of the machine that prints that description. Right? That's exactly the code of that thing. And then I'm supposed to feed that through its first argument to the actual machine whose code you handed me. And of course, I'm not outputting machines, I'm outputting descriptions of machines. So the whole thing is inside angle brackets. Now, of course, there's a fundamental thing which says when you hook things up like that, you can either describe this as A composed with B and then hooked into T, or A composed with B pre-hooked into T. They're exactly the same picture. So this is kind of an associativity property. It says, well, inside the angle brackets is where the action is happening. So it says this is exactly the same as P put this in parentheses just to emphasize. So I can certainly rewrite it like that. Right, I'm just rebracketing it because this says feed this and this and this. Well, I can group these two together first and say do this and then feed that into T. But what is this? Hey, that's just A and B. That's A. And B. And as before, I'm feeding it into T. But is this not the description of R? What did I say R was? And this is what we see is coming out as the output at 2. So that is 2. The output of B is exactly R. So what is 3? So little t is describing whatever t computes. And what are the arguments to little t? The code of R and W. Okay, so I have explicitly shown you the machine R. I've done this fairly trivial calculation. And it says R does exactly what it's supposed to do, which is run T on the source code of R with W. So you see, it's nothing magical happened. But now the ability to access your own source code is built into ordinary Turing complete programming languages. So there are lots of people who got really excited by this kind of stuff. There was even a thing called reflective programming, which is people writing code that says, this is the code that inspects its own source code and, you know, modifies it. And so people started writing so-called reflective programs, which take inputs from the world outside and then look at their own source code and modify it. And this was one of the early ideas of how machine learning should work. Because the idea was machine learning, well, here's a program, it's learning stuff. As it learns, it should modify itself. But of course, now we know this doesn't really work on any large scale. And this has been blown out of the water by statistical learning theory. But still, it was an attractive and fundamental idea in early recursion theory, or as it is now called, computability theory. Okay, so that's one of the great theorems of early computability theory, the recursion theorem. Let me prove an application. So this may be of some interest to people interested in the practical side of programming languages. Supposing we say there's this set called min_tm. And it says, it's the codes of Turing machine. So no Turing machine with a shorter description recognizes the same language. Okay, so you would like to say, look, I want for every possible algorithm or every possible computable function, the shortest description possible. And I want to collect these in a set. So clearly, for all algorithms, there is some shortest program. The trouble is this set is not even CE. Okay, so we'll prove this by contradiction. Suppose min is CE and E is an enumerator. For it. So what E does is it keeps spitting out Turing machine descriptions, and every one of those Turing machine descriptions belongs to this set. And eventually, any given machine that's in this set will be produced by E, and nothing that's not in this set. Okay, so that's what it means to say it's computably enumerable. Maybe I can't decide whether something is in this set, but I can enumerate all its elements. I'm going to show you that even this is not possible. So it's a highly complex set. You can't even approximate it computably. So define R as follows. So what you do, step one is obtain R. So this is where you're using the recursion theorem, right? You're saying there is some Turing machine that works as if it has access to the source code of R. So obtain R. Okay. So then you say run E and wait until you find a Turing machine M sub I such that the length of the description of M sub I is strictly bigger than the length of the description of R, which is the Turing machine you're defining. So you're writing down the source code of R, and one of the things you're using in the source code of R is obtain R, and you know that this is just a temporary step and that the recursion theorem will eliminate it and produce a bona fide Turing machine. So you have the description of R concretely, you now wait for your enumerator to produce something strictly bigger than R. And now what you do is run mi on W and do whatever mi does. So that's R. The language of R is exactly the language of mi because of this last step. But length of the description of R is strictly less than length of the description of mi. And this is a contradiction because mi is supposed to be the shortest, the Turing machine with the shortest description that has the same language. Okay, so the recursion theorem leads this to an immediate contradiction. So anytime you say, in fact, any criterion of optimization that you might have, you might say, I just want the optimal programs according to this criterion. And yes, you might fantasize about that, but forget it. It's not even computably enumerable. Now, the recursion theorem is actually a fixed point theorem. So fixed point theorems, diagonalization theorems, and all are all grand instances, or all instances of one grand super theorem. So I'd like to state it like this theorem. So this is using the terminology of yesterday. If G,
sorry, Professor.
yeah,
Marino asks, is min co-CE?
is min co-CE? No, I don't think it's either CE or co-CE. So off the top of my head, I don't see the argument for not co-CE. If G is a Gödel universal function, and sigma from n to n, so again, we've gone from strings to integers, is a total computable function. Then there is, remember, this is an existential quantifier. There is some n such that for all x in n, g of nx equals g of sigma nx. So you can basically see what n does and what sigma n does is exactly the same. It's going to be codes. There'll be different algorithms, but they'll be computing the same computable function. Okay, so this is basically a version of the recursion theorem. So both the recursion theorem and this version of it and the previous version of it were proved by Kleene, who is one of the giants of computability theory. So he didn't start it. He wasn't on the list of, post Markov, Turing, Gödel, Church, but he was Church's PhD student, and he pushed the subject tremendously far. So this was, I think, his PhD thesis, proving the recursion theorem. So look at what this thing is saying. So I've stated it in terms of integers, but it just as well works from strings to strings. If you think of codes as strings and not as integers. Now you say, give me any total computable string mangling function. Anything. It takes an input string and mangles it somehow, but it's done in an algorithmic way and in a total computable way. Then there exists some program such that when you mangle it, the output will be another program that computes exactly the same thing. And when stated like that, it's pretty mind-blowing. So people have asked me, well, what about if my string mangling program just inserts arbitrary rubbish in the middle of the text? And I'll say, yes, well, there's some program that will put that arbitrary rubbish in quotes and hence compute exactly the same thing. So I don't think that's a good putative counterexample. But you can imagine more drastic things, rearranging stuff and all, yet there is some program that when you do all those rearrangements and so on, you get something else. It's a legal program, but not just is a legal program, it does the same thing extensionally. So that's the Gödel universal version. So I didn't put the proof of this, which is like 3 lines long, on the web page, but if there's enough demand, I can do that. So this pretty much wraps up what I wanted to say about the recursion theorem. So we'll draw a line here. And after this, I'll take a break till 11:45. And then we will do Gödel's incompleteness theorem. So I stop sharing and I okay. Welcome back. Let me check the time, 11:48. So remind me, the class technically ends when? Is it 12:55?
Yeah.
Yeah, good. So what I'd like to do now is talk about Gödel's incompleteness theorem. So he proved 2 very fundamental incompleteness theorems and 1 very fundamental completeness theorem. So he proved completeness of a proof system for first order logic. And then he proved incompleteness of a system, of any system for arithmetic. And then he proved that no formal system can prove its own consistency unless it is inconsistent. Because in an inconsistent system, you can prove anything. Okay, so people get confused about proof versus truth. And people often say things like, well, they confound these concepts. So I tried to make this clear in my discussion of first order logic. There is this notion of some kind of mathematical structure. You're making statements about that structure in a formalized language. And these statements might or might not be true about that particular structure. They might be true of one structure and false of a different structure, etc. So there's a notion of truth, which is the connection between a formalized language and a particular mathematical structure that that language talks about. Then there is a different concept called proof, So first order languages just have a notation for terms and formulas, but first order proof systems or logical proof systems have a notion of deduction. So they have a notion of axioms and rules of inference. And then they have this idea that starting from the axioms and using valid rules of inference, you can ultimately construct what's called a proof, and proofs are given a precise formal definition of what constitutes a proof. The important thing about a proof is it is mechanically checkable. So you cannot mechanically discover proofs of all things, but you can, given a proof, you can mechanically check, is this a correct proof or not? At least in principle. So in fact, what people in mathematics call formal proofs, for example, things that are published in math journals, are actually not in the logical sense really formal proofs, because for one thing, they're certainly not mechanically checkable. You need experts to read them and check them, and experts who have already a lot of insight. So a lot of stuff is left out of published mathematical proof. There's a lot of effort these days in mechanizing mathematical proofs, mechanically checking them. And people have done quite significant things. So of course, the four-color theorem was famously the first one that had a mechanical proof. And now this has been fully and rigorously mechanically checked. And there is a very, very famous guy in Paris called Georges Gontier. Georges Gontier is a very brilliant young Quebec-born mathematician. He actually went to McGill for one semester, and apparently he told me he was in the joint honors math and physics program, and he decided this was too trivial. So he moved to Paris, where he worked on logic, programming languages, and semantics, and is now, I think, the head of the Microsoft lab that's working on mechanical proofs. So recently, they completed the proof of the Feit-Thompson theorem. I don't know if you know the Feit-Thompson theorem. It's one of the landmark theorems of finite group theory. And it says, very simply, all groups of odd order are solvable. And this theorem won Thomson the Fields Medal. And it was a famous proof because when it came out, it was 270 pages in published form. And it was one of those classic proofs that said, let's assume that this is not true. 270 pages later, they had a contradiction. So this, as you might imagine, was a nightmare to completely mechanize and check. Anyway, let me go back now and talk about arithmetic, or as it is more often called, number theory. And I mean it in this formalized logical sense of number theory. So here is the structure that we're talking about. So there's a particular mathematical structure. It consists of the natural numbers, and it has the usual things. It has variables, it has operations, it has function symbols, plus, times, it has relational symbols, namely equality, it has quantifiers, and it has Boolean connectives. And if you want, we can. And it has punctuation marks, like parentheses. Okay. And given this structure, you can actually define new predicates. But in some sense, these are just macros, but you can define them. So x less than equal to y is defined to mean there exists z such that x plus z equals y. Okay, and you can define x strictly less than y is defined to mean x less than or equal to y and x not equal to y, and so on. So you can start out with this basic stock structure, and then you can build up many more things on top of it. For example, you can even define int div xyqr. So this is a 4-place predicate. It takes 4 integers and it's defined to mean x is equal to qy plus r and r strictly less than y. So this means y divides x with quotient q and remainder r. So here's a typical 4-place predicate of elementary number theory that you can write down in logical form. And so you can imagine you can do lots and lots and lots of logic and lots and lots and lots of things in number theory. You can define what it means to be a prime number. You can define all kinds of things. So this is the structure. Now we have, we call this T of A. These are the true statements about this structure. Okay, this is called the theory of N, the set of true statements about the structure. So you see, this is a particular mathematical structure. We reason about it kind of semi-formally or using fancier language than just number theory to do our meta reasoning. But then you can also talk about, so this is kind of a semantic concept, but now you can talk about an axiomatic framework. So you can write down an axiomatic framework and people can propose many different ones. So here is one very popular one. It's called piano arithmetic. So I emphasize what was before a semantic notion grounded on algebra, and it is there is a specific unique structure corresponding with that I have just described. Piano arithmetic is just an axiomatic framework which we have to interpret in this structure. So piano arithmetic is basically you take first order logic plus you add a bunch of axioms. For all x, it's not true that x plus 1 equals 0. For all x, y, if x plus 1, if x plus 1 equals y plus 1, then it implies x equals y. For all x, x plus 0 equals x. And when I say first order logic, I also mean all the facts that equality is an equivalence relation and so on are implicit. Associativity of addition. Commutativity of addition. Zero is an annihilator. And then this kind of law and I haven't checked this out myself, but I believe associativity and commutativity of multiplication can be proved. And then you add this thing, which says phi of 0, and for all x, phi of x implies phi of x plus 1. All this implies for all x, phi of x. So this is, of course, induction. And you can either view it two ways. It's either infinitely many axioms, but in a single scheme, or you can put a for all phi and make it second order. If you stick with, so there are all kinds of meta theorems that have been proven. I think I may be not 100% correct, but something like this is true. If you try to write down a first order finite axiomatization of number theory, you can always construct a non-standard model in which you will have weird things like an infinitely large number, which is of course not there in the standard model. So if you really want to write down the standard model, you're forced into this induction scheme or into a second order piano arithmetic. And then of course, we have built in some rules of inference, which says, this one is called modus ponens. And this one says, if you've proved something with a free variable x, then it's universally quantifiable. Okay, so if you construct a proof in piano arithmetic, you get a theorem. So a theorem is something that you can prove within a proof system. So the word doesn't make sense unless you specify the proof system. So you say, my proof system is piano arithmetic, and these are the theorems of piano arithmetic. And this fundamental soundness theorem for piano arithmetic says this. The theorems of piano arithmetic are included in the true statements about the standard model, which is a damn good thing. It says, if you've proved something, you can be sure it's actually true. If you prove something using piano arithmetic and these rules. Okay, if you make up different rules, who can tell whether that's true or not? So you will have to prove a soundness theorem. So this tells you, in some sense, a kind of safety property of piano arithmetic. These are certificates of truth. Now, here's a fact. Theorems of PA is a CE set. And why is this true? Well, proofs are very concrete, finite objects. And you can write a program that constructs proofs one after the other, extending them, and enumerates all the proofs in the end. And every time you enumerate a proof, you look at the thing that you proved and you output this as a theorem. So the list of theorems of piano arithmetic is a computably enumerable set because each theorem comes with a finite proof. Okay. And now we're going to prove this theorem in a the collection of true statements of n is not CE. And I'm going to spare you all kinds of coding details. You can get some of these details from Dexter Cozen's book on automaton computability. But in some sense, it's not difficult to imagine how this goes, right? Because we've done val comps before. We check things with a stack, but we know strings can be coded up as integers, and it's not difficult to code up in number theory things that say, find me the third symbol in this string by suitable encodings of strings as numbers. So things like checking valid computations is doable. So the key point is we're going to show the not halting problem mapping reduces to the theory of n. You see, this is not a statement about any specific one proof system. It says there's no computably enumerable way of enumerating the true statements of number theory, which means forget it. You can't find a proof system because the essence of a proof system is that proofs are finite and whether something is a valid proof or not is mechanically checkable. So any proof system you have has to be a computably enumerable set, has to enumerate the theorems of that proof system, has to be a computably enumerable set. And we're just telling you this thing is not a computably enumerable set, so don't look for a proof system that's going to get all of it. Okay, so what we're going to do, we must construct a formula of number theory. So let's say we call this formula gamma of number theory such that, you see the importance of giving a name? Because otherwise my sentence would have gotten completely out of control. So there's a particular formula gamma of number theory such that if you give me the encoding of a Turing machine and a word, this thing belongs to the non-halting problem if and only if gamma is true. So this will constitute a mapping reduction. Okay. So how do we do this? The point is we can encode valid computations of a Turing machine in number theory. So it is a thing that looks like this. Valcomp MWY says Y is a valid computation of M on W. And actually, Dexter writes down explicitly how to say this. Okay, so, but it's all just coding up things in arithmetic. And we've already seen enough coding, but you can probably believe it by now. And once you've done that, we can simply say gamma is defined to be not there exists Y. Valcomp MWY. Okay. And this is an explicit total computable construction from M and W. this formula. So this is a formula of number theory using the encoding of strings as numbers. And otherwise, it's exactly the same conceptual picture as what I've already shown you for valcomps. You have to check that everything. So now it's not a question of can I recognize it with one stack or two stacks. It's like, can I write a formula of number theory? So, so yes, you can actually write down a formula that says each configuration follows correctly from the previous one according to the rules of this Turing machine M. And you can write down that the start configuration has to be this, and there has to be a hash mark in between, and so all those things you can code up without a lot of pain in number theory. And this completes the mapping reduction. Okay, so this is the end of the proof. And so this is, of course, not how Gödel proved it, because these are all much more modern concepts. But this shows no finitary proof system can capture all true statements of number theory. In short, no proof system can be complete for number theory. Okay. Right. But of course, while this is a nice proof in our modern sense, using our modern technology, it's actually useful to look at the ideas of Gödel's proof. So, so Gödel did some absolutely magnificent masterpiece of encoding. So he showed, first he showed one, every formula can be encoded as a number. So we call this thing Gödel numbering, and we use the same ideas to say, oh, every Turing machine can be encoded as a number, every this, that, and the other combinatorial structure can be encoded as a number. So every formula can be encoded as a number, no matter what the formal system is. The way he did it, became very clear that it's anything with a finitary description can be encoded by numbers. So this is called Gödel numbering. Okay, so we will write this. If phi is a formula, we'll write this for the Gödel number of phi. So this is a formula. Then he showed, given any proof system, so there are two pieces to Gödel's brilliance. One was the technical details of all these encodings, which he did correctly, even though people like Hilbert were freaked out and were sure it was wrong. But also the vision to do this, because before Turing and anybody else, before Church, Turing, all the computability people, he came up with this stuff in 1931. So given any proof system, he showed how to define a formula that expresses provable Okay, so if a formula is provable, he showed how to define a predicate in number theory that says the formula described by this particular Gödel number is actually provable. So this is a sensational thing that you can do that. Sensational to get it all right. Intuitively, not so sensational because you say, look, the fact that it's provable means I can construct a proof in some finite way. A proof has to be a finite object. Okay, but he showed there is an explicit construction of this provability predicate as a formula of number theory. And then he proved the really sensational thing, the fixed point theorem, which says for any formula psi of x with x a free variable, there exists. So you see, this is a for all. So when you write down a proof of something of the form for all there exists, what have you done? If you've given a constructive proof, you've constructed an algorithm that takes the input that satisfies the for all and produces the thing that satisfies that there exists. So he actually gave an explicit construction to do this. There exists a sentence, a formula, which we will call theta, such that, so this notation means it can be proved in your proof system that theta is equivalent to psi applied to the Gödel number of theta. Ooh. So you can see why I call this a fixed point theorem. Somehow it says, you give me a formula theta, you give me any psi, and I'll find a theta such that when you apply psi to that theta, of course with some Gödel numbering happening along the way, what you get back is basically the same as theta. So basically what this thing is saying is theta says my Gödel number satisfies psi. Psi is a predicate, right? It has one free variable in it. So you can stick things in there and ask, now that I've stuck something in there, is that instance true? And now we are almost done. Because now he says, okay, apply lemma. So this is called Gödel's lemma. Apply this lemma to the predicate not provable x. Okay, so this has got a free variable x sitting in it. So apply this lemma. So what does it say? We get a formula, which I'll call, I don't know, rho, such that rho is provably equivalent to not provable Gödel number of row. So it's this whole thing that's provable. I'm not saying that row is provable. This whole equivalence is what's provable in your proof system. But what does this say? So first of all, row cannot be provable. So let's see why. So what are the possibilities for row? Maybe row is false. We don't know. Let's investigate. So supposing row is false, then not provable Gödel number of row is false by the soundness of the proof system. Oh, well, if that's false, then provable Gödel number of row is true. And by the correctness of his provability predicate, so row is provable. Then by soundness of the proof system, row is true. Because it's a very basic early theorem that anything that you actually prove in your proof system is sound. So it must be true. But we assume that row was false. So this is already a contradiction. Okay, so then row is true is the only other possibility. Then row cannot be provable. And there you have it. True statement, not provable. So there exists a true statement of number theory which cannot be proved. So people say cannot be proved, but of course it means cannot be proved in the specific proof system which you are using. Then you can say, oh, well, obviously you're using a broken proof system. You should beef it up. The trouble is everything he did is very generic. So you say, okay, well, I'm going to augment my proof system by adding, these 7 new axioms and these 12 new rules. And he'll say, okay, I have to change the provability predicate, but it'll apply to the system that you've just newly constructed. And he does it in a generic enough way that you can see, doesn't matter what the proof system is, he can always write this provability predicate. Now, so people often said things like, well, why don't we just add this unprovable thing as one of the new axioms? That'll unfortunately just create a new proof system. You can do all this construction again, and you'll come up with a new formula. And you can keep trying and adding, and it won't work. So basically, unless you say all the theorems of number theory are all the true statements of number theory are my axioms, you're not going to get a finitary proof system that's going to be complete for arithmetic. Okay. Tarski proved something even more difficult. So a predicate defined in number theory, actually, no predicate defined in number theory can capture the truth of arithmetical formulas. So now he's not talking about proof systems. He's just saying you try to define a predicate that's called truth, and that says truth applied to the Gödel number of a formula should just be true or not. I'm trying to say, can I define this predicate in number theory? And this theorem, due to Tarski, says, no, you can't. And the basic idea is we have an arithmetic hierarchy, right? And that arithmetic hierarchy applies to formulas as well as to computational problems. So we can say a formula, you can have a basic formula and then you can put quantifiers on it, right? So any arithmetic formula will be, so the point of a formula is that it's a finite thing, will be at some finite level of the arithmetic hierarchy. So it cannot capture truth of formulas at higher level. So Gödel said the true things of number theory cannot be captured by any finitary proof system. And Tarski said you can't define even what the true statements are of number theory within arithmetic. You have to be outside it. Of course, this raises the question, are there things that are interesting to professional number theorists that are unprovable? And after, anytime a problem becomes very hard, people say, gosh, maybe this is one of those unprovable things. But then usually somebody comes along and proves it. It may take 357 years sometimes. But in terms of what's, interesting statements in number theory to the professional number theorist, we don't really have examples of things that have been shown to be unprovable. This is not the case with analysis. Many interesting questions in measure theory have been shown to be independent of the axiom of choice. So analysis is a different story than this. Okay, that is the end of the course. I still have a few minutes left, so maybe I'll open it up to questions, but maybe I'll also say a few things about the final exam if anyone's interested. Maybe I'll stop sharing so I can see you. Does anyone have any questions about this or about the final exam? Actually, I've forgotten what's on the final exam. I've stopped screen sharing, right? So I can safely look at it. What is on the final exam? So it's a take-home exam. You have to answer using LaTeX. There are 1, 2, 3, 4, 5, 6, 7 questions. Question 1, the total, let's see, what is the total? 10, 20, 40, 55, 70, 90, 100. So 100 points for the final. The first question is something about the first part of the course. So, you know, DFAs, NFAs, Claney's theorem, regular expressions, etc. Second question is also about that. Third question is about decidability and undecidability, but it is about decidability and undecidability questions about languages, regular and context-free and things like that. So you have to give either algorithms or reduction arguments for why something is undecidable. Now, when you're giving a reduction argument, the things that we have proven undecidable already, you can take for granted. So things like the language, the problem of whether the language generated by a context-free grammar is all of sigma star, we know this to be undecidable. So you don't have to reprove that. I don't want to see long proofs of things that I've already done in class reproduced on your final exam. Okay, so PCP is undecidable, you take that for granted if you need to. Val-comp's construction and how you use it to show things are undecidable, take that for granted. And you can just say, you know, using Val-comp's blah, blah. So these are all intended to be relatively short answers. I will take points off for long answers, even if they're correct. So you write 3 pages of crap, and you know the last paragraph actually contains the right answer, and there's lots of gibberish in the middle. I will take points off because clarity of expression is part of what you are learning. Right, question 4 is, oh yeah, I'm going to give you a language and I'll say, tell me what kind of language this is. Regular, context-free, not context-free, and of course you have to prove whatever you claim it is. Question 5 is about decidability questions. Question 6 is also about decidability questions. All these things should have relatively short answers. And question 7 is true, false with no explanations. So 5 true, false questions. You just write true or false. Some people think that if they get the wrong answer, but they give some explanation, they will get some points. That's not the case. I will simply mark you true or simply mark you depending on what you said in the end, and not on reasons you give. Sometimes people give the right answer and then I read their explanation, I feel like taking points off. I won't do that, but it is a warning. So are there any questions?